I'd like to start thanking the organizer for inviting me to this really nice workshop. I apologize before I put my voice. I lost my voice over the weekend. It's coming back, so I hope it will last for 30 minutes here. I want to continue the talks from this morning about twisted matter, especially talk about twisted bilayers. I'm just going to have 2 layers. And talk especially about superconductivity and a nematic state that we find in twisted bilayer graphene, and contrast that to a possible chiral state that might be found too. So what I want to do is to show some modeling we've done on magic angle twisted bilayer graphene, trying to capture the superconducting phase. And we're going to make one assumption, and that's where the pairing comes from. But I'm going to try to argue that it's a very realistic assumption to do, assuming the pairing comes from electron-electron interaction. And sort of phenomenological assumption, but based on sort of physical properties of graphene. And show you if you make this one assumption, so this one free parameter, we can get a very intricate superconducting state, actually, twisted bilayer graphene. It has both sort of modulation on the Moria scale, but also on the atomic scale, and they are both D-wave nematic states. And this state it can be nodal, but it can, depending on filling, also be fully gapped. So it's sort of both depending on the filling. And then if I have time, I want to contrast this to what would happen in monolayer graphene. So if you do monolayer graphene and you do a very similar or the same approximation for the pairing, you always get the chiral D-wave state. So one question that we always had is like, why isn't the twisted bilayer graphene giving us the chiral state? So I'm going to try to show you what's happening in the short stories. There's very strong interband pairing in twisted bilayer graphene, and the chiral states suffer from low energy subgap states. And neither of these happens in dope graphene, but it happens in the twisted bilayer graphene. But before that, I'd like to thank everyone who actually did all the hard work here. The original work was done by my previous PhD student, Thomas Lötman, together with Farvas Karhiskar and Johan Schmidt. And the recent work that actually is already, is a work in progress right now, is by my current PhD student, Lucas Baldo, together with my senior researcher in my group, Patrick Honvall. And without funding, none of this would, of course, be happening. Particularly grateful to the Wallenberg Foundation and the ERC for this project. Okay, so we already heard this morning about twisted bilayer graphene, so I'll go pretty quick through here. But if you take 2 layers of monolayer graphene, you twist them with a certain angle, you get this really nice Moria pattern. And what is really nice and interesting is that if you get at certain small angles, or they tend to be small, because in principle be bigger, but you get very flat energy bands. So the band structure completely flatten out, and you get these flat bands. So this is trying to just illustrate this, sitting at this magic angle, that you get a very flat structure here with very distinct peaks in the density of states. So the graphene spectrum is here blown up 1,000 times. You see these are very tall peaks in the density of states. What's also important to keep in mind is that the density of states vary a lot in the Moria cell. So you have a very high density of states in the AA region and very low in the AB region. It is still some electrons in the AB region, but you have a very pronounced peaks in real space where you have these peaks in the AA region. So that's going to be important because, as you can imagine, the superconducting state responds to where the carriers are. So if you have a lot of carriers, that's where you get a lot of pairing as well. So we already saw, I believe, this picture from earlier this morning, but there is superconducting domes found at the magic angle and twisted bilayer graphene. And there's several domes, and interspersed with what seems to be some sort of correlated insulated phase. And there's also been results seeming to find, at least in twisted bilayer graphene, superconductivity in a range of fillings. So it's not just around plus, minus, or minus 2, even though there you have the highest. So this is different experiments at different angles, measuring TC for superconducting domes. You see there's a lot of superconductivity here, but essentially throughout the band filling of the Moria spectrum, you do seem to have small domes of superconductivity. And there has been a lot of speculation saying, well, maybe this is actually very similar to the high temperature cuprate superconductors. There's this superconducting domes, there's some correlated insulated state, it's very strong coupling, there seems to be a pseudogap state, or some strange metal state, and there's other properties here. I'm not going to talk so much about that. I'm going to use a type of modeling that if you do it on the square lattice, you get the nodal D-wave state. So we can use that directly to compare, but otherwise I'm not going to touch so much with the similarities with the cuprates. Okay, so how do we model this? Well, we sit down to say, well, yeah, we can take an effective model and we can model the A sites and do some effective modeling. We have to make sure we get the appropriate bands and appropriate topology and so on. But they said, all right, well, why don't we actually, instead of being a little unsure which approximation we do, why don't we actually model all the carbon atoms in the system? So that's what we set down to do. And the normal state is pretty easy to model. The intra-layer is just graphene. So there we have, it's enough to have a nearest neighbor hopping. In each, so L here is the layers. You have two layers, and in each layer I have just nearest neighbor hopping. I have some chemical potential that I can shift my doping in the material. And then I couple these two layers with this interlayer term here. So you have a couple layer 1 and layer 2. And I can calculate this hopping parameter with, as exponentially decaying because there's later factors. They capture the bond angle dependence. The first fascination, at least to me, in this material is that you need a lot of interlayer bonds to accurately get the normal state. So to capture the intralayer physics, you just need nearest neighbor. To accurately capture the Morea spectrum at the magic angle, you need around 250 interlayer bonds per atom. So you have very long range, 6 nearest neighbor, you need to go across, and the distance between the layer are bigger than the distance in the plane. So this at first seems very strange, but this is what you need to do to get the accurate band structure. And the accurate band structure in our case looks like this. So here we zoomed in on the small energy redeem of the Morea band structure. So you have 4, they're spin degenerate, isolated flat bands. So we get, so here's the bands here, and we get small band gaps here to the other states. And here you see the density of states, and it's high throughout, but there also are clear van Hove singularities in there. And we also can see that this clearly is a magic angle dependence here. So here we plot the peak height as function of angle, and so it clearly peaks here at a specific angle. That's where you get the flat spectrum. And if you plot the charge density in real space, it looks like this. So this is one. This is the Morea cell, and we see that they have a lot of electrons sitting here. This is the AA region, and we don't have much electrons sitting in the AB and BA region. Okay, so that was a normal state. And then to capture the superconductivity, I need to make some assumptions, because we don't know what's driving superconductivity. I could assume it's phonons, but I'm going to assume it's coming from electron interaction. The question is, how do I capture that? Well, we choose to go back to actually thinking about what is the physics in graphene. So in graphene, you have nearest neighbor hopping around 2.5 eV. And there is an on-site repulsion that's actually rather large in graphene. It's around 6 to 10 eV. So if you compare U over T, you are not in a weak coupling regime. You're in some intermediate coupling regime just for single-layer graphene. Now, in single-layer graphene, you don't see much interaction physics because you don't have any density of states. But here I have a system where I should have the similar interactions, and I have a lot of density of state at 0 energy because of the flat band. So the question is still, you're in an intermediate interaction regime, and the question is, how do I handle that? It's very hard theoretically. We choose to say take a rather phenomenological approach and say, well, graphene is actually just the infinite limit of aromatic molecules. Think your benzene rings. So those are formulated as p-pi bonded plain organic molecules. And for them, what's really important is that you have good nearest neighbor spin singlet bonds. You need to favor those over polar configurations. And if you do that, you actually get very good estimates for a number of chemical properties in this material. And if you translate this aromaticity picture that chemists use into physics language, this is Pauling's resonance valence bond idea. And if you write that in physics language, it looks like this. So you take two sides next to each other, and you favor the spin singlet configuration. So you take this one minus this one, which I can just express as a creation of a spin singlet. And incidentally, if you were to do this on the square lattice, this is the simplest way to model a nodal D-wave superconductor on the square lattice. So we're going to take all this together, and we're going to solve a mean field theory. It's complicated enough because there's a lot of atoms. So I'm just going to say I'm going to have a favor of this spin singlet bonds, which I can write like this in mean field theory. So I'm favoring a spin singlet bond with an order parameter. And I'm going to solve set consistently for this order parameter. In the end of the day, I only have one free parameter, and that is J. That is only favoring the spin singlet bond. That's the only free parameter I have. And then, before we continue, it's important to understand what are the possible symmetries I can get from a superconducting state. So I have an order parameter that can sit on all bonds in the material, and I have three different bonds in the honeycomb lattice, 1, 2, and 3. And that means I can have three different symmetry solutions. I first have the S-wave solution, like technically an extended S-wave. It has the same order parameter on all three bonds, like this. And if I transform it into K-space, I get a solution that have the same sign in all of the Brillouin zones. So this is an extended S-wave. Then I have two more solutions. There are two D-wave solutions. One in real space looks like this. So you have the order parameter twice as big on this bond and have a minus sign on the two other bonds. Fourier transform that to K-space, and it looks like a dx squared minus y squared. And then you have a dxy version 2 that looks like this in real space and like this in K-space. So that's why we call it dxy. These two D-wave solutions, because they're four-fold symmetric on a six-fold symmetric lattice, is actually degenerate. They belong to the same irreducible representation. So you can very easily combine them. And the simplest combination is to have a chiral combination, take D plus ID. And in real space, that looks nothing else than you take the 3 cubic roots of 1 as your bond order parameters. You have the bond order parameter 1, e to the 2 pi over 3, and e to the 4 pi over 3 here. And that is the solution that we get on the monolayer graphene if you do the same thing. And it's rather simple to understand why you get the chiral D-wave. Because if you take dope graphene, you have this band structure, this graphene with a Dirac point here, and it's doped just it here, say, up in the gray region. It's a single band picture. I can think of my quasi-particle energies just following this form here. So this is just the kinetic energy and the order parameter. If I sit on a Fermi surface, this is 0. And then if I want to gap out all my states, I want to have an order parameter that doesn't have any nodes. And the simplest one is to take my 2D wave solution and just combine them in a chiral fashion with an I here, because nowhere except the gamma and the K points is this an order parameter that has any node. So this is a fully gapped state, and that is indeed the state that wins in any self-consistent calculation you try to do on the monolayer. So this is just a number of results, more than 10 years old at this point, but showing with a range of theory that you always get this chiral D-wave state if you assume some nearest neighbor pairing or even longer range, as long as it's not on site in monolayer graphene. So you always get this chiral state.
Yeah. Does the state have a surface state in the gap, or is it topological?
Yes, it's topological. It has a short number of 2 or 4 if you count the spin, so it would have surface states in the gap, yes. Okay, so that was the story about graphene. So now I want to take essentially the same thing, but I want to solve this on the Nematic and twisted Bilayer graphene. The problem is it's 11,000 atoms, and I have to calculate the order parameter on every single bond in the system. So it's very computationally intensive, but one can do it if you're a little clever on how to solve it. I'm not going to go through how we solve it. in any detail, but we essentially expand the Fermi operator in a rational pole expansion, and you end up in the end of the day with a set of linear equations that we can solve in parallel on some big computer somewhere. So that's how we solve the system numerically. But what's more interesting, I think, from a physics point of view, is actually what the results are. So here is the critical temperature as function of coupling strength. Remember, I said there was one single parameter I had in my calculation was this J. So I often have to tune things as a function of J because I don't know what J is. If I'm in single A graphene, J is actually, it's a critical coupling to reach superconductivity, and that sits in this region here. But in the, if it's Bilayer Graphene, I have a lot of density of state, so I get the final T's at a lot lower temperatures. And it turns out that the leading order belongs to the two-dimensional irreducible representative E, and it's this green color state here. And it goes down to quite, you have to have a rather small coupling constant here, and you still get a substantial critical temperature. So you can get high TC in this two-fold degenerate solution. And if you look at the two solutions, they look like this. Don't focus on the arrows. I'm coming back to the arrows, but focus just on the color scale here. So this is the order parameter in the top layer, and the bottom layer is actually just pi shifted, so it's the same. It's two dimensions, so I need two solutions. I have one solution that has a clear axis like this. I call this delta x, and then I have one that has a clear axis like this, delta y. And you see, I have a lot of order parameter in the A region, as I expect. That's where the electrons live. But also here have clearly broken rotational symmetry. Remember, the normal state had no broken symmetry, so this is a superconducting state that breaks the symmetry. So this is the first, this is a Moirier-scale nematicity I get in the sample as for looking at which solution is best. And if you look a little bit more carefully in this, we can get out even more information. So TC, technically all combination of delta x and delta y is feasible, so you can write things up in sort of a combination like this with some angle theta and phi, and we can see which solution wins. And this is where we find the nematic solution. So here I plot the energy difference at t equal to 0 when I change phi, and when I send, theta and phi. And the best one is the one here in the corner here. And that is one where theta is 0 and phi is 0, so that is a nematic solution, so it's just delta x. But if you plot along here, you can see that in the color scheme here, but you can see it here, it's rather small energies, but you see that you have a variation of the energies, and you have actually 3 distinct degenerate ground states. So the nematic state can point in 3 different directions, so they're all degenerate. This would be expected. You can start with a 6-fold symmetry to have that degeneracy. And it's all real. I never get a complex part in this order parameter. What's actually interesting is if you were to take this state here, that is the worst state, this is the perfect chiral state. It's actually the state that was best in graphene is the worst state here. And it is the symmetric state, but it has the highest energy, so this was a state that would absolutely not happen in this case. So that was the Moirier scale nematicity on the whole Moirier pattern, but I have atomic scale resolution, so let's see what that gives us. So I can go and see what are the individual order parameters doing. And I can decompose the order parameter into the different individual d waveforms. So you have dx squared minus y squared and dxy. This was an S component, if you remember. The S component is essentially 0, so I'm not going to plot it, but we did calculate it, but it does not show up. So I can just compose into this on each bond, on each atom. I can look at what is the local d-wave symmetry, and I can technically plot this by just forming a vector field for the d-wave order. So depending on how it points, it points out which type of d-wave do I have locally. And we do that, and that is what these arrows I told you to ignore were. The arrows is the vector field that shows you which nematic state do I have. So here, for example, you have a nematic state that points in this way. So this is dx squared minus y squared. But if you go away from this region and you point up like this, it goes, for example, up to the dxy square. So I have a local d-wave order that rotates in the Moria field, and it even forms sort of some vortex structures here. And these are not superconducting vortices, it's vortices in the nematic order parameter, the nematic vector. So there's no associated phase winding of the order parameter here. So this is what we get on twisted bilayer graphene. And again, I would like to compare it with, if I did the same calculation graphene, I would get the chiral d-wave state. And if I did it on a square lattice, I would get a nodal d-wave state. So in some sense, twisted bilayer graphene sort of does a little bit of everything. I get a real value d-wave order, but it can't decide which d-wave order it wants, so it sort of change them throughout the units. You can actually pick up nematic signatures in densital states, but you have to be a little careful. You have to do it sub-lattice resolved. So this is data on the sub-lattice A in each unit cell. So we plot then the density of states here as function of this angle, going along these arrows here. And in the normal state, number 1 and 3 and number 2 and 4 should be equivalent. But as you see here in the density of states plot, they are clearly not equivalent. So this is a signature of the nematicity broken in the superconducting phase. But if you were to plot things in sublattice B, you would get the opposite. So if you average the two sublattices, you do not measure the nematicity in real space. But you will be able to see it if you sublattice resolve the structure. So it's a nematic and sublattice dependent the state signatures at least. Okay, so that sort of summarized what we found. We're just making one assumption about the pairing. We assumed it was electron-electron pairing, and it's the simplest possible pairing that you can get or model when you go above S-wave pairing. So simplest anisotropic state. And it's surprisingly complicated. You both have this Moreski nematic state, which breaks, let's give you this clear symmetry break in this direction. But also if you look at each atomic scale, I have a variation between the two d-wave solutions, which don't happen in graphene. And there's also some signature of the nematicity in the density states. So you see, we did this a couple of years ago, and that was interesting and so on. But we always sort of wonder, okay, how much have we assumed things, and how does it fit with experiments, and how does it compare? And what was always at least bothering me was why twisted bilayer graphene was so different from monolayer graphene, why it behaved so different. So we have gone back to these questions a little bit more recently. So what I'm going to flash is it's working. We're writing it up, so I don't have all the answers, but I have some answers to why it's so different from the chiral state. But first, to sort of just put this in a little context of what other people have done. We already saw some very nice work this morning, and you saw some of these plots, I think, even this morning. But there seems to be data from experiments pointing to a nematic state. So this is showing the nematic axle in the different superconducting domes here, extracted from magnetic field dependence on the resistivity. And there's also fits to STM data on trying to fit the S-wave and the D-wave state. There was a discussion about which gap it fitted, but in the end of the day, I think it was a nodal state proposed either way. And clearly, if you have a nodal structure, it's unlikely it's going to be a homogeneous S-wave state, right? So this seems to be, based on this, we'll say, okay, it's likely nematic and it's likely a nodal superconductor. In terms of experiments, there's a whole bunch of different results on various effective models, and also with different pairing assumptions that we're trying to go through a little bit a few days ago, sort of just to highlight a few different results, as I'm going to put them on here. This is just some of the more recent work. So this is one work who found nematic nodal superconductivity, and they assumed an interval C to T invariant order. And if they assume that the pairing is spontaneous and nematic, they could say that they had nodal superconductivity. So they assumed nematic and got nodal superconductivity. Here's another work that assumed a rather different pairing. mechanism of weak phonomediated pairing, very similar to some buckyballs, dope buckyball systems. And they also found a nematic D-wave spin singlet state with some nodal structure. So again, seem to be rather consistent with what we found, but with a very different starting assumptions. Here's yet another paper already from this year who looked into what's become known as a heavy fermion model for twisted bilayer graphene, and if they assume big inter-eigenband pairing, they could find stable nodal superconductivity with a nematic order. So it seems to be popping up nematic order and nodal in a lot of different models. So we were interested in see, okay, so what does our results say? Can we put them a little bit more in the context of these other results? And we had data for all 11,000 carbon atoms. It's good in some sense because we have all the data, but it would be good to understand it a little bit more in terms of the mirror physics. So we took our solutions we had and we projected them on the Moria bands and see what we get. So here is a nematic D-wave projected on the Moria scale. So we have 4 bands, and I have here label them as B. Let's see, I don't know if it's visible. Say B plus, B minus, T plus, and T minus is the bottom and top, and plus and minus are the Valley index. And the chiral state is here, and try to use a color scale here. So you see these ones are all real valued, and these ones are complex, they wind around. So you see the chiral keeps on 6-fold symmetry. The nematic has either, let's see, this is dx squared minus y squared, and this is dxy. But what is interesting is this sort of patchwork of where I get the solution and where I don't get the solution. And it has to do with certain bands pairing. First of all, I only pair between different valleys. This is good because it means I pair k to minus k, so I don't have any zero momentum. I only have zero momentum pairing, no finite momentum. But I also have very strong interband pairing. So I pair between different values. I always pair plus and minus, but I also pair up the upper Moria band with the lower Moria band. I'm trying to color code it here. So the purple is pairing the upper band to the upper band, but the green boxes here pairs between the Moria bands. So I have strong pairing between all the bands I can have in the Moria structure within a zero momentum pairing regime. And that really means that this simple argument I had before, while I would get chiral D-wave state, is not as simple in twisted bilayer graphene because I have interband pairing, very strong interband pairing. So this simplistic picture is like, let's have the chiral D-wave state because it's only gapped state. That argument goes out the window. This is not relevant anymore with so strong interband pairing. It doesn't mean the chiral D-wave cannot happen, but it means it's not naturally favored over all the other D-wave states. So this is the biggest, to me, the biggest difference between the twisted bilayer and the monolayer, well, within the assumptions I'm doing, is that you have so strong interband pairing, and it's always there. Then we looked a little bit more at the band structure because I haven't actually talked to you about what is the structure of the nematic state. So here I plot the nematic, the band structure along some, actually I haven't even written this, but it's along some high symmetry lines in the Brillouin zone for increasing order parameters. So this is reasonably big order parameters. We're trying to just illustrate what happens. And you see I crank up the order parameter and the spectrum gets more and more gapped. There is some sharp features here, and sometimes they go down and they truly touch zero energy. It depends on which resolution and the nodes are along the high energy axis that I plot or not. So often the nematic state has nodal quasi-particles. Sometimes it can miss the zero energy portions, and I actually have a fully gapped spectrum. But often it has some nodal structure. The surprise to us come when we plotted for the chiral wave, exactly the same thing. And as you see, there are states here that never gets gapped. The states that keep sitting in the gap here. So I have 2 of the Moria bands that never that never gaps in the structure. And this would, if you want to say, if you saw this and said, well, which one does the material choose? You would clearly say it's going to choose a nematic state because the chiral state is stuck with zero energy states. Why the chiral state has zero energy state, we don't fully understand. It's probably tied to some of the topology of the band structure. But they are always there, and it's really tied to some order parameter features, some phase winding of the order parameter. Yeah, but with that, let me just summarize what I've been talking about. We have modeled superconductivity with a bilayer graphene using an atomic scale, fully self-consistent approach. We made one assumption about the pairing. We assumed there was pairing on nearest neighbor bonds. Following at least what I was thinking phenomenological argument for where the interaction is coming from. We get a Moiré scale nematic ground state that is threefold degenerate. So I spontaneous break rotational symmetry in the superconducting state. I don't need to break it in the normal state first. But I also get an atomic scale nematic D-wave symmetry. So I have sort of nematicity on the two length scales in the system. This state is most often nodal, but it can be fully gapped. And it's, as you see, very different from monolayer graphene, where I would have a fully gapped chiral state, and then the cuprous, if I did the whole thing on the square lattice, I would get a nodal D-wave state, and there would be no competition. So by just changing the atomic structure of the system or making this big Moiré cell, I actually get a very different superconducting state with the same assumptions. So with that, I thank you for your attention.